before we start, I'd like to know you a little bit and to warm up this presentation. So let's do some knowing each other, at least on the technical stack. How many of you are like doing Docker and containers? And I don't want to see hands. I would like to hear one clap, just to have an audible signal of the audience. So Docker. All right. Kubernetes. Yes. Spark. Spark on Kubernetes. All right, great. Thank you very much. Awesome. Today I want to talk to you about how to transform Kubernetes, how to make it and shape it to your own purposes. And for that, I am using the topic that we are doing, the project that we are doing on transforming Kubernetes into this platform that allows us to run streaming workloads. And everything started with this container, that revolution of being able to pack your application and run it anywhere. I guess that was the tagline of Java that so many years ago, built once and run everywhere. Now I think with Docker we are a bit closer, but then you need to start, once you start doing this a lot, you need to get grips of how this happens. And Kubernetes is giving us a level of management on top of those deployments, but there are moments where we feel we need more. We need more capabilities, we need better ways to automate the things, the applications that we are deploying. We need better ways of gathering resources to build up the stack that we need to run our business. In today's presentation, I want to share with you a pattern. I think that's what it is, a pattern of the operator, and how you can apply it to harness the power of different components that are available out there on Kubernetes, on the open source space, to create the coordination and automation in Kubernetes that you require to deploy your own application. I'm Gerard Mas. I work for Lightbend. As we mentioned before, we are the company behind Scala. I personally have been involved in the Scala community, and in particular in the Spark community since many years. And I've also been a participant on Cassandra for a while. Those are my coordinates if you want to reach me. And I'm also the author of Stream Processing with Apache Spark, together with my co-author, Francois Garillo. It's out there since June, so if you want to know about the stream capabilities of Apache Spark and the two APIs, then that's a book you should get. Okay, end of the ad. Lightbend, so you probably know us for Scala, for Akka, for Play, those open source frameworks out there. We also work on data systems, and we have been promoting the fast data architecture for a few years now. That has been evolving into this comprehensive chart where we are supporting a number of runtimes, streaming engines, and on top of a number of providers on-prem and on cloud. In particular, I'm working on that top layer there that's called Lightbend pipelines. We'll probably change that name because everything is a pipeline these days. But what we're doing there is coordinating actually the deployment and runtime of those applications. And some of the lessons learned on building that component is what I'm going to share with you today. So we were talking about containers, and containers gave us three very important things. A way of packaging an application. This is completely self-contained. You can take it and run somewhere else without worrying about dependencies other than other systems. We have immutable deployments. Once you created your container, that container doesn't change anymore. There are ways to hack that, of course, but if you are playing by the rules, that container will restart every time from a known state. And one rule that you should live by is a single responsibility principle, where each container is only running one process, one intended use for it. When we start using those, then we see this is very practical. I can run my HTTP frontend, I can scale up my HTTP frontend, I can scale up some of my microservices, I can deploy more microservices, And at some point in time, you start creating chaos. So that previous chaos that you had to deploy and launch VMs and services and whatever is now turning into the different chaos on how to manage those Docker containers and make sense of all the deployments. Most of them are manual or done by some scripting guru in your organization. Then everybody knows when he or she goes on holiday. Then there is Kubernetes. Not the first one of those cluster managers out there. So we had Yarn and we had Mesos. But probably what Kubernetes is doing right is that it comes with a set of services already out of the box. So you don't have to worry about, for example, Marathon on Mesos to start deploying something. There are built-in APIs on Kubernetes. So once you give them an image and some descriptor file, it will know how to run this into a cluster that is enabled with Kubernetes. And more important than that is that cloud providers are adopting Kubernetes as a standard mesh to deploy applications. So if you're running Kubernetes on a Minikube on your laptop and you develop something, it's running there, you can take it to GKE, you can take it to Amazon, you can take it to Azure, and you know that it will run eventually with some tweaks here and there. Okay, so now that we have this great platform, let's say a space where we can develop our applications, we start deploying things. And we see that our deployments start growing again. A great tool gives us some means to do more. And with that additional power, we start again developing and deploying applications. And at some point, we will want more. So Kubernetes is great for scaling things that are stateless, whereas having stateful applications, things that require storage, things that require checkpoints, like databases, like streaming systems, are a tad harder to achieve. And like the basic construction blocks that you have, deployment, a stateful set, and a pod, might not be sufficient to have your applications, your full application deployed. For example, what happens if you are, we're all doing streaming in this track today, and we have been hearing about Kafka. So many times you need to have a couple of Kafka topics. Those Kafka topics are running on a broker. The broker might not be running there. How do you create it? Will it be part of your deployment? If it's not, then you're breaking your pattern, and you will need something additional, something on the side to deploy your application in fully. That's the role of the operator. Operator is there to extend Kubernetes to things that it didn't understand before, things that it didn't know before. So Kubernetes knows about services, knows about pods, knows about endpoints and ports, but it might not know about a Kafka topic. So what do we do if we want to add that concept of a Kafka topic in Kubernetes? A Kafka topic will need a broker, will need some storage. And in addition to that, it will need to be deployed on more than one broker because we want replication, we want partitioning. It's not a really trivial thing to do. Same thing with databases. What happens with databases, with replication? How do you run a distributed database, something like Cassandra, on a system like Kubernetes? So the operator pattern was actually coined by CoreOS. Is a way of extending, of actually using the Kubernetes API to tell Kubernetes there is an extension point now. There is some new application that, or a new capability that we want to add on Kubernetes, and it becomes native to it. So like you can do get pods, then the next thing you can do is get my own resource. It's a way of actually encoding the knowledge that you have in your organization to deploy applications. And that's very powerful, because instead of relying on humans around us, humans might get sick, might move on, might want to do some other stuff, you can encode that knowledge into an operator and have a reproducible deployment of your application time and time again. Not only that, but the operator is also able to listen, to observe the environment and the things related, the events related to your application, and evaluate those. For example, what happens if one of my topics is not available anymore? What happens if one of my pods went down? Well, there are levels there. For example, if I have a deployment, maybe that pod belongs to a deployment, so the deployment will take care of it. But my operator might take care of the deployment. And that sort of, let's call it recursive responsibility, makes it a very reusable pattern. But we have that observe, things that happen in my cluster, in my environment. I get events. Once I have the event, I evaluate the event. What do I need to do with this? Oh, there is a pod that went down. I need to act. Maybe I need to launch a new pod. I need to migrate some component, etc. How it's done? Well, there are few components. So here is like the verbatim definition of the operator. There are two things with an operator. There is a controller, and there is a description of the resource that is offering. And that system gets then implemented in some software and some structure, some schema that gets deployed into Kubernetes. The function of an operator can be reduced to a streaming application. So that observe, evaluate, act loop can be then implemented using a streaming processor, for example, that is listening to events, that is processing those events and generating some actions. Both sides are talking to the Kubernetes API, and you get your input, you decide what to do. You produce an action on Kubernetes that will change the environment, and you will receive potentially some more events. This is an example of one of our own implementations. You see it's kind of readable in the Akka Streams DSL. We are watching this pipelines application custom resource, so all the events related to that. We are also sending those events to a parallel event called the event flow. And I am going to log some of the events that are happening there. I am going to track some metrics, so I am injecting there the capability to have some visibility, some monitoring. And eventually, the most important part is that we are going to transform or to act on that event and transform into an action. And once we have those actions, we can execute the actions, send them back to Kubernetes. There are many APIs, like SDKs out there in the Golang community. There are like 3 or 4 different operator frameworks that you can use to bootstrap the deployment, so the development of your operators. You don't have to like code yourself the event listening and the watchers. You just code like the core of your application. We are doing this in Scala. We use I can't recall the name. Maybe I can recall it later. Some API to talk to Kubernetes implementation in a Kuber implementation to talk to Kubernetes from Scala. Operators, so you don't have to deploy everything or develop everything yourself. There are many operators already available out there. So you can just take them from the open source and deploy them on your cluster to augment it with capabilities like database like Cassandra, a workflow system like Airflow, another database like Elasticsearch, run batch or streaming computations on Spark. You can deploy brokers and topics using the Kafka Operator. There are more than one out there. There is more than one out there, and so on and so on. There is a comprehensive list on the link provided there. There are many, many more. And we are just moving the goal a little bit. Now we have operators that can do stuff for us. How do we take advantage of the new functionality? Before I go there, I would like to give you a bit more insights on how the operator works. So there are 2 sides to one operator. One is the custom resource definition. It's a schema that defines or describes the new resource that you are adding. And once you have added that custom resource definition to Kubernetes, then you can talk directly to that custom resource using instances, like you had classes and objects. You have then the custom resources where you say, I want this or I want that from you, custom resource. And let's see how that works in a small example. This was previously a live demonstration, but now it's migrated to the P shell, that's the presentation shell, where everything is just pasted into these slides. I hope you get the gist of it. So we can do get CRDs using kubectl, and the CRDs will list the installed CRDs on my Kubernetes cluster that I am connected to. This is one of our test clusters. What do I see here? I see that my cluster has a number of CRDs already deployed or installed. We have Flink support installed there. We have the Kafka Operator. StreamC that comes with a number of different facets. So there we have a Kafka Connect and a Kafka Bridge. And for us, of the most importance is the Kafka Topics operator, so that we can create new topics and manage those topics once they are deployed. We have that pipelines application, that's our custom operator. I will be talking about it a bit later during this presentation. And the Spark operator, also it comes with two sides, one that is dedicated for batch processing. That's the scheduled Spark applications where you can say, please run this at some moment. And the Spark applications where you can say, okay, run this. And we are using it to run streaming workloads. Let's have a look at one of them. How does it look like? So here we have the Kafka topics from StreamC, and we can request its description. So please, let's get that CRD described in YAML. And it's a very long YAML, because it's specifying validation rules, it's specifying how you call that resource, and it's also specified how the instances of that resource are called. Important, very important for us is this names stanza. It's telling us how we can call this resource using a standard kubectl. All right, so let's do it. Let's say kubectl get Kafka topics. That was something that Kubernetes didn't know before. Once we install that CRD, that new capability is available in Kubernetes. We can get it like any other resource in Kubernetes. And there we go. I have a number of applications deployed, and there I have a list of topics that are deployed in my cluster. There is this other side of the description. This side of the description, the spec, it says how you need to declare an instance of that resource so that the resource or the controller for that operator can understand it. And what it's saying here is that I need to have a specification with partitions and a specification with replicas, and there is a little bit more after that. I just don't want to overcrowd this. And this is very similar to what we would do using the Kafka API. We would say I need a topic, I need so much replication, I need so much partitioning, and Kafka will connect to the broker and create it for you. So let's try to do that. Here I have a definition using the YAML file for a user's topic. And what it's saying is, well, I specify there some metadata to specify the namespace where I'm deploying this. But then I have the topic name, the number of partitions, and the number of replicas. Also with some additional configuration for the retention time and the segment size, whatever that is. I apply this. Again, like any other resource, you see here the pattern. Now I am talking into Kubernetes native interactions, Kubernetes native API. I don't need to learn about the Kafka API anymore. I just need to know about the specifics of this YAML file. I created my users topic, and now if I list it, it's there. So I have now a Spark users topic. It has 3 partitions and 2 replicas. What is striking, and I hope I can bring that message to you, is that to do this, I don't need to install the Kafka API on my machine. I don't need to have the binaries for the create topic. I don't need to write a program that says connect to the broker with this configuration and create this topic programmatically. No, I did it declaratively. I just have a small YAML file that says this is the topic name I need, this is the partition, this is the replication. And I give it to Kubernetes, and Kubernetes gives me back a resource, like gives you back deployments, like it gives you back a pod, right? Keeps giving. A good friend. And it's augmenting the capabilities that you have in your hand to create applications. Because now you have a new trick under your sleeve. You can create an application that does streaming, and when you deploy that application, you deploy the logic and you deploy all the needed resources to run it. So now we have a Kafka topic resource. I showed you we also had the Flink operator deployed there. I have the Spark operator deployed there. The next question is, oh, they are doing great things for us, but how do I harness that power? How I can put it together so that I can create an application that is comprehensive, that can take pieces and can put together, actually like Lego blocks, put together pieces of every one of those providers of services, and create something that solves a business problem for me. And that's what I called operator federation. That's the idea I come today to present to you. Here I start with one example, and this I'll be liked about it. It's how the Spark operator works. There is a controller there. The controller understands this YAML file. And the YAML file for Spark is a little bit more complex than the one we just saw. But it's saying this is the Docker image that we have. These are the different configurations that I need, et cetera, et cetera. The operator controller will do a submission to Spark, and Spark will deploy this into Kubernetes. The interesting part there, when you start looking under the hood of how these things are working, is that Spark itself also implements a operator pattern inside Spark to be able to deploy those executors on Kubernetes. So it's also going to go to Kubernetes and say, I need pods to run this executor. And I need so many because these specifications say I need to replicate, for example, to 20 cores. So I might need 10 executors with 2 cores each. That kind of negotiation is done by Spark and not by the Spark operator. So there is already some cascading effect there. The operator says, I need this application running, and Spark says, I need these components running. Also, the monitoring and how you react to events is then having a cascade effect, or having a kind of contained bubble of responsibility. The Spark driver, that is a part of the Spark application, will be taking care of monitoring the executors. If one executor goes down, it will receive an event, it will spawn a new executor, it will say, here are your binaries, please execute this task, so it will become part of that Spark cluster again. The operator doesn't need to know about it. From time to time, it will say, give me your health, and I want to know how are you doing in terms of runtime and in terms of the number of executors you have, but that's about it. We have a sphere of responsibility, and we don't need to take care of that, which allows us to increase the level of abstraction. So now we have the Spark operator. I give you my application, and you take care of deploying it. It gives it to Spark, and it takes care of keeping it running. Very interesting. But if I want a streaming application, then I also need my Kafka topics, or maybe some entry points, maybe some HTTP endpoints that I want to deploy to gather data from the outside. And what I would like is to have something that knows my application, that has some insight on my application, and is able to deploy all those components and infer that I need those, and keep them running. So that custom operator there will be getting events of what is happening with the Spark operator. Is my Spark application still running? Has it go down? If it went down, please restart it, but I can also execute actions to it. I can also scale it up or change it and configure it. How are we using this let's say, in real life? We have developed a system that actually harnesses together your development environment using SBT, the not really simple build tool, with some additional components. There are some plugins, we are able to compose the application and say, this is how an application looks like. And then might be built of different backends. You can say, I want all my front end done. We are doing it with Akka HTTP and Akka Streams. So I want to deploy a large front end to have some HTTP endpoints where I can gather data from my IoT devices or whatever out there. And then I want to process the data using Flink or using Spark, and I want to produce it used to a database or to some other system. Then I can use all my Alpaca connectors from open source. I can plug them there and use them to produce data downstream. To show you how that works, I'm going to introduce a simplified use case. This is inspired by real life. One of our customers created this application actually by hand at the beginning to process call data records. So this is a telecommunications operator. They have data coming from the fields, actually from the masts or the antennas out there, reporting the connectivity of cell phones. And they do some aggregation on top of that data that is produced to Kafka and to some HDFS backend. So that flow internally there, it goes through several Akka Stream processor, and all the aggregation is done in Spark. Using the streaming framework to produce the aggregations that go to HDFS and to Cassandra eventually. We abstract this concept on saying, all right, first of all, everything, the communication between the things is driven by schemas. This is very important because it tells us what is the data and what the shape of the data is that is going between components. You can validate it. You can know my application end-to-end is consistent, and is consistent with the data I'm providing to it. You can also filter at the start of your application, the start of your pipeline, and say, this is data that I don't recognize, so it's not entering the rest of the application, not having a chance for corrupting any subsequent element there. This concept of streamlets is a component. You could compare it to a small application that contains the business logic written in the backend of your choice. So you might be using Flink, you might be using Spark, you might be using Akka Streams. We don't kind of build on top of our API. It's really clean the API of the provider. And what we are doing is providing a way to build this, to package this into Docker containers, and link them together and deploy it. Now I am back on my magical shell here. It's amazing. It takes forever. It doesn't need even to run because you can edit it. This is my project, and that project that implements this use case has a number of components implemented as sub-projects. So I have an ingester there that takes the data. I have an aggregation output that is putting the data somewhere else, is producing it to the downstream systems. And I have a data model declaring all the data that is being shared within the components, and the Spark aggregation that is contained in that business logic to aggregate those calling records. Next to that, I have this concept of a blueprint, and I think that's a name that came in the previous presentation. So all these concepts are somehow linked. But the blueprint is saying this is how those components are linked together. This is the relationship. It's a direct acyclic graph defining how the data flows from one component to the next. So I'm saying here that the generator one out goes to a merge. So there are two generators going into a merge. There is an ingress that goes to the merge, and then the output of that merge gets validated, and whatever that's valid goes to the aggregation, and whatever that's invalid goes to an error or a dead letter queue. Then using this extension of the build, I can build and publish. Build and publish does two things at the same time. First, it builds your whole project, all the binaries of the project, compilation phase, normal compilation phase. And at the end of it, it generates a Docker file. And the Docker file contains the binaries for every single component in your application, but also information about this blueprint now transformed into what you could call a deployment plan. This is what I need to do to transform those little applications, little components, services into a comprehensive end-to-end system. Now I can go and deploy this to a Kubernetes cluster that has my operator deployed there, and then the deployment starts. Here I am running on OpenShift, and on-prem, it's understandable more or less. But what we can see there is that now I have an application that has been created. There are a number of pods being launched there. And after a minute or two, all the pods are active and running. So I have deployed an application that is composed of 3-4 different stages, like an atomic action. And that atomic action is actually being taken care of by the operator itself, relying and delegating responsibilities to the different other sub-operators, could I call them, to realize the independent functions. I need topics, so the topics have been created. I need to launch my HTTP services. I need to have, an HTTP ingress for each one of them, so those are obtained from Kubernetes. Now I need to launch a Spark, and when I launch a Spark, I also have some executors that are there. Then you can extend this concept and say, I now want to have a concept of scaling up. What is this? This means very different things for different frameworks. If you want to scale Cassandra, you need to do something different if you want to scale Kafka or Spark. But the scale for your end user becomes an abstract concept, but I can say, I just want more capacity, and I say there, my aggregator needs to grow from whatever it is now to 5. So I do this, CDR aggregate to 5, so the previous one is terminated, the new one is launched, and then the new 5 executors are launched. You see here that the way of deploying this was to remove the previous one and deploy the new one. There's a Spark. If we were deploying Akka streams, we'll just increasing the deployment, and so we will have, like, if we were previously 3, we will have like 2 more, and that's it. Then what is, then, let's say, the next trick is that as the operator is coordinating all these different actions, it also can inject some of its own logic on every deployment. And we are using that to inject the Prometheus rules for exporting metrics from every one of such components, giving us the capability to first have a complete view of the topology. That's what the chart you are seeing there. That's how the application looks as a full deployment. And on the other pane, you see the performance of one of the components now that I have clicked there. So this is the input and output throughput of that particular component. So in a nutshell, what we have done is taken that concept of the operator and have extended it through a model of federation. Now we create our own operator that is in charge of handling work to other operators. We have few design principles in this application. One is this blueprint. It tells you or gives you a map of how things are connected together. Very important, because you cannot infer that from any other element there. Schema-driven keeps you sane, because you know what the data in, what the data out is from each one of the elements, and it also increases the ability for you to reuse any component. You know what the data they require, you know what the data they produce, and they can be composed with each other. We have been using and extending the build tool to do things for us, so we don't have to write YAML, or the developer doesn't have to write YAML. It's auto-generated for you, because from the blueprint and all the code that you have written with some introspection, we know what you want to achieve this on the deployment side. There is a CLI. What you saw in the kubectl is a plugin there, a CLI that allows you to interact with Kubernetes, and the operator clue of today's presentation is it puts all those pieces together. This is code that you write. This is knowledge that you transfer from your sweat, your tears, and your brain into some code, and you have it then running and working for you 24/7. All right, so there's a thought that I leave to you. We use this to implement streaming workloads, but you can reuse the same system to do your implementation for your travel, trips, manager, whatever the business you're in health, in travel, in insurance. You can find ways of how to reuse that pattern to your benefit, and I hope that you do. There are some resources there. The operator, the Kafka operator we're using, Confluent also has one. And if you have questions, I think I have time for one. Otherwise, you can. Yeah.
Thank you for the talk. So I was wondering if, because you said the system is schema-driven, I was wondering if it supports the schema evolution as well.
Sorry, if it supports?
If it supports changes in the schema.
In which schema?
So the whole system you had, like, is a schema-driven, you validate all
yes,
the steps?
Yes, of course. Yeah, there is a schema migration. So there are two ways of supporting that. Compatible schema migrations is what we recommend. When you extend your schema to add new fields, those fields become optional so that the existing state of the system still works, and you don't need any migration. If you really do a breaking change in your schema, that the schema is completely incompatible, then you will be forced to introduce a component that translates the previous schema into the new schema. I think that's what we are doing at this moment. Thank you.
Hi, so you said that in your controller, you delegate the creation of Spark-related things to a Spark, basically. So when you deploy the controller, you deploy it with an instance of Spark running, or is it talk to other instances of Spark running?
So I don't know if I can find this quickly. Probably do. So what happens here, the Spark operator it also implements the same pattern. It's also a controller, and it listens to Kubernetes events. So you don't use a Spark command like a Spark submit, but you instead throw a YAML to this thing, a YAML that describes your application. And then the operator there will take the YAML and the specifications within it to really create a Spark deployment. And that's what's happening behind the scenes. So if you see here where it's a bit broken up, I would say, the controller, what it does is takes the YAML and transform that YAML into the submit parameters. There are subtleties there. There are, for example, if you are using streaming, you also need a checkpoint directory on a shared storage. That shared storage is created before this, so we are also doing it from outside the controller here. But that's what's happening. So every controller takes responsibility. It's a hierarchical organization, takes responsibility for what happens underneath, for what happens with the things that it creates and it manages.